out where you can get those as well. All right, go ahead, Dave. What were you gonna say?
Okay, Bill, I just put a link in the chat. If you want to open that and share your screen, please.
Okay, let me go back now to the share. Okay.
I want to bring your attention to a program that we offer that it runs through the academic year, Saturday morning astrophysics at Purdue. This is a program for middle and high school students. Grade levels are 7 through 12. Most of the students that participate in the program are middle school students. We have very few high school students, so it's mostly grades 7 through 9. Bill, if you will scroll down, I just want to bring folks' attention to the opportunity for, I know you're not in school now.
Keep going down.
Keep going, yeah. I know you're not in school now. Bill, you can stop there. But if you make a note of this website, there are, excuse me, there are some lessons resourced further down, but I just want to point out, if you pass this along to your students when school starts, our first session will be toward the end of September. They can join the fall 2022 wait list, and when registration goes live, I will email the people in the wait list, and they'll have the first opportunity to sign up. This is done remotely. It's not on campus. We've tried it both ways, but I honestly get a much more satisfying response when we do it remotely. So I've had students from all across the US, Hawaii, Canada, Cambodia, India, China. And so it's a really great opportunity. I have a group of about 12 students from a school, excuse me, a school in Medellin, Colombia, South America. So it's a diverse group and it's a lot of fun. And I just want you to keep it in mind for your upcoming students. Also, Bill, if you, never mind, I can see it here. There's a SMAP YouTube channel. And when I say SMAP, that's Saturday Morning Astrophysics at Purdue. We have some videos there. We have interviews with grad students. We have some lessons. We have labs. We have recordings of previous sessions. We do this in Zoom, and some of the Zoom sessions are recorded, and you'll find them there. I am also very happy to share any of our resources with other educators. And so there is a link there, the last green tab, Teachers for SMAP. And if you would like to be notified of things we do and have access to our lessons, please go ahead and sign up. And the bottom two links are some previous things we've done. So plenty of opportunities there. If I can answer any of your questions or help you with resources, please let me know. Astro is one of our more aggressive programs here at Physics and Astronomy Outreach. So with that, I think, two other things. When we left this morning, and we had the bolts in the water, we talked about maybe using multiple bolts or a larger bolt. Ravi pointed out to me after we left that in terms of heat transfer and mass and size of the objects, it would be more effective, more efficient to use. Hold on just a minute. Come on in. No, come in. There's the material. There's the list. Would you please go through the list and check off everything that's here? Okay, thanks. Multitasking today. It will be a more effective heat transfer and more efficient if you have multiple smaller bolts than one larger one, because it takes more time for the more surface area, the more effective it'll be. So larger is probably not as good as multiple. And let's see, one last thing. Starting the afternoon session, I have in my teacher notes for this lesson, we're going to do melting ice. Actually, Ravi is with me here again, and Professor Ritchie is wandering around back there, and he'll take over here in a little bit. I wanted to point out that we're going to do melting ice. Ravi actually kind of wrote this lab and came up with the idea. I referenced a couple of NGSS standards here, and the standards that I referenced are relevant to everything we've done today. So standards PS3.B, the amount of energy transfer needed to change the temperature of matter by a given amount depends on the nature of the matter, the size of the sample, and the environment. And that is relative to everything that we've done and will do. Secondly, energy is spontaneously transferred out of hotter regions and into colder ones. And we saw that this morning. We're going to see that again here as we start this afternoon. So I did try to link what we're doing to, and I know some of you follow state standards and some NGSS, but I think that the concepts that we're covering are relevant at multiple levels. So, Ravi, I'm going to turn over here to Ravi. He's got a little device that you want the external cam, or do you want to be on the computer?
I think I'll do this. I'll try this.
Okay, we'll go to the cam number 2, and we'll put Ravi on stage.
I think I'll do this way. So that. Yeah, I think that's better.
Okay, so tell us what you've got, what it does, and what you're going to do.
How much time do I have? How many minutes?
5 minutes.
5 minutes. Okay, let me go. So you have here what's called as a hand boiler, and there's a liquid here, and there are 2 bulbs. So the liquid can flow from one bulb to another. Okay, now I'm going to hold the bulb at an angle, and you can see, you can put some comments there on what you notice. I hope you can see. Yeah, some of you have some comments there. Some of the teachers have some comments. What's it called again?
It's called
a hand boiler.
Hand boiler. So we provided one of these to the teachers that received materials. Ravi, hold that level for a minute, and let's put a white page behind there. Okay, now, so Ravi's going to hold one end. This way? Sure. And without hesitation, you see the liquid jetting into the other end, the other side. And it continues to gurgle a little bit. Ravi, reverse the direction. I'm going to do that. Okay. So, what do we learn from that? What concepts could you use from this little demo to engage your students?
Transfer of heat, high pressure to low. As the hand warms the bulb, it moves the liquid. Substance has a low boiling point. Heat transfer, particle motion.
Okay, I think I would buy into all of those things. So it is a volatile liquid in there. When I say volatile, something that has a low boiling point, it evaporates readily. I'm getting a head nod.
I think so. I think it's just getting larger amount of volume to the. I don't think you're actually boiling the water.
Oh no, we're definitely not
so
boiling
it's
the
not boiling
liquid. No. So
it's just got a low surface tension.
When we say a hand boiler, we need to point out the water is not boiling. What we're doing is heating the air inside one side, and it's forcing the liquid to go to the other side. So there's heat transfer from your hand to the glass bulb. The heat then transfers to the air inside, and the increase in pressure of the air causes the liquid to flow to the other side. So there's no boiling involved. So I don't want to convey that. So it's
So the
nothing.
question is, the liquid inside water?
No, it's not water. It's a volatile liquid of some kind. I would guess it's some kind of a organic, let's say it's alcohol.
It's ethyl alcohol.
Okay, it's ethyl alcohol.
Yeah.
So it's a low surface tension. Maybe.
So Dr. Sidama had a question. Why not water? Why do we use alcohol?
Yeah, good question. Why don't we use water? I mean, it's rather delicate. Kids are going to break this. They do. They're kind of fragile. They're also not real expensive. But why don't we use water?
Are there some responses?
Bill, any responses? Why don't we use water?
Responses, yeah, David. The boiling point is different than alcohol.
That is definitely true. Water boils at a much higher boiling point. It has a lower vapor pressure than alcohol.
The water would not move as drastically. Water, the molecular attraction between molecules is stronger in water. But if you said it isn't actually boiling, question mark, then how do you explain how this works again?
Okay, so it works by, see, one side is empty. And when Ravi holds the one side, the empty side, I'm sorry, he holds the side with the liquid in it. His hand transfers heat to the glass. The glass transfers heat to the vapor inside. Well, I maybe said air earlier. It's not air, it's vapor from the alcohol, but it's a gas. So he transfers heat from his hand to the gas. That increases the pressure, causes the gas to expand, and that forces the liquid to the other side. And it bubbles, but it's not boiling. So it's the effect of the pressure of the gas on one side pushing the liquid to the other side.
The color, I think, is artificial. Could have any color.
Sure.
I don't think ethanol has a color.
No, it's artificially colored.
So it's got to do more with the vapor pressure then. So it's volatile and it quickly evaporates and fills the space inside. I think with water, it may not be this dramatic.
If it was water would still have vapor pressure on both sides. So would it work as well with water?
I think the vapor pressure would be less and the effect would be less dramatic.
Well, if it worked as well with water, they would be using water instead of alcohol.
And also, if you look at it carefully, alcohol doesn't stick to glass. Water would stick to glass. No, it's the thermometers we use are spirit thermometers.
Mm-hmm.
They don't wet glass.
So there's maybe less.
Like he mentions surface tension.
Mm-hmm.
I think lower surface tension is another reason why they use alcohol.
You could say lower surface tension. I would say higher vapor pressure.
Both, yeah.
So this is, I used to have one of these on my desk when I taught high school, and kids would come up and, they come into class. It's one of those things that you can have out, kids come up and play with and wonder why. And it's always a good way to engage them with something they don't have otherwise. Okay, Ravi, your 5 minutes is up.
Yep, thanks.
Okay, so I'm going to go on with the experiment, and I'm not going to go on screen. I'm going to have Ravi adjust the camera so that to show what I have on the desk here. Leave it up high. Leave it higher. Yeah, leave it up higher and aim the camera down. Up higher. Raise it a little higher. Okay, a little closer. I'll move these a little closer. Okay, I have three materials here. I have a block of aluminum and a slab of aluminum. These are all about the same size, about 4 inches square. I have a piece of acrylic plastic, and I have a piece of plywood. And the question that I pose to the students is this: if we were to place an ice cube simultaneously on each of these three surfaces, on which one would the ice melt more quickly, the most quickly? And sometimes they'll come up and feel them. And those of you that actually have these materials, what do you think?
100% response.
On which one do you think the ice cube will melt most quickly? Anybody want to hazard a guess?
They do. They're saying aluminum.
That's
Better-
funny.
Better
That's-
conductor of heat.
Yeah, okay. I'll say that's funny because your students will always predict the opposite. They'll
Well,
always-
and someone
Yes.
said the wood because the surface temperature is warmer to touch.
Exactly.
Yeah.
So, in fact, when you touch, and the kids will touch each of these, and they say, "Oh, the metal feels cold, and the wood feels warm." I might ask them to explain why the wood feels warm, and they probably will not have an answer. If you have a digital thermometer that will read without touching, we can actually
See the temperature.
take the temperature of each of these. Now, this is again, if you receive the materials, you have one of these. I'm just going to
Okay,
show
so
you.
maybe you can try from this side. I can
I-
see the reading.
Okay, I'm just going to point it to the laser on each of these surfaces and show that on the wood.
Maybe they can see. Ask them. Maybe I can. Can I hold?
You do it.
Can you see the temperature?
Yes.
Yes.
You,
Yes.
what's it say?
21,
Yeah. Look at the next one.
22, 25.
Strange.
Okay. Now this depends on the angle that you aim. I did this a minute ago, and they all read within about 0.3 of a degree the same. So they have different reflectivities and different surface properties that maybe affect the temperature. So I kind of move it from one side to the other more head on, and I'll get certainly within 0.5 degree, the same temperature for all of them.
But it's certainly not colder.
But it's certainly not colder. It feels colder, but it's not colder. So I'll ask students, in fact, in the handout, we start with, why does ice melt? And kind of, again, we're back to the particle nature of matter again. What happens when ice melts? Then I ask them to write down as many science-y terms that they can think of that relate to the process of an ice cube melting. And I do that so we get some vocabulary out on the table. I will have kids come to the board and write these down. And that's when we can have a class discussion about the terms they're using. So,
David,
yes,
and I'm going to chime in on this part. You both were touching the metal one a lot, and I think that caused a raise of temperature. And someone asked, they should be the same if they're sitting at the same room temperature, right? And the answer is yes. They should
Sure.
be.
yeah. So we could give the students, I constructed the lesson to make it a little bit open-ended so that we're not telling students to do this step 1, step 2, step 3. I didn't want it quite as cookbook style. So the lesson says brainstorm to the students, brainstorm with your group members how you could conduct an experiment to figure this out. And so we'd give them a little time to do that. Would have them make some predictions. And then you as the teacher could suggest what they do if they don't have an appropriate procedure, or let them try it and learn from what they do. So what we would anticipate is we'll take an ice cube, equal size ice cubes, put them on pieces at the same time or as close as possible, and see what happens. So there's one on the aluminum, plastic, and wood. Now, one of the things I say to have handy is a toothpick or a pencil or something to hold the one in place, because it'll tend to slip around a little bit. If your tables are not any more level than mine, it'll slip around. But we're getting quite a puddle of water here on the aluminum.
Can they notice it? Check with them.
Bill, can you see that puddle of water?
Yes.
Okay. And the ice cube is about half the size that it was a minute ago. And the wood and plastic, not much happening. So which one of these materials is, so why is it melting faster on the metal? Let's start with that. I think somebody had this in the comment a little bit ago. I just want to reemphasize.
Say, because it's a conductor.
Metal is a good conductor. So we've already in the previous experiment calculated the specific heat of the metal and found out that it was lower than, for example, water. We never talked about the specific heat of wood, an entirely different material. So think about this. If compare the specific heat, we talked about the temperature change with water relative to the temperature change of a metal under the same conditions. What about wood? Would wood have higher specific heat? Now, wood is not a homogeneous material. So I recognize that, but as a composite material, or as a heterogeneous mixture of materials, would wood have a higher specific heat or lower specific heat compared to, let's say, the aluminum here? Anybody want to hazard a guess?
Lower.
So, I can't, I probably shouldn't even use the word specific heat with wood because it's not a pure material. And when we talk about specific heat, I think generally we're talking about a pure material. So I'm using the word in a general way that, well, may not be exactly correct. Which one is the better conductor?
Between what?
Between the wood, the metal, and the plastic?
The aluminum.
Aluminum's the best conductor of all three. I've got a little puddle of water here on the plastic and pretty much nothing on the wood, although the wood might be absorbing a little water. But if we go from metal, plastic, wood, I think we see that the metal is the best conductor, has the lowest specific heat, relatively speaking, and the wood would have, based on the amount of water forming, the wood would have the highest specific heat. Now, that may sound confusing, but think about what we did this morning with water. It took more energy, more heat energy, to change the temperature of the water. Meaning the heat energy does not flow into the water as readily compared to the metal, where it flows quite readily. The metal is a good conductor.
And good comment, there's lots of air trapped in that plywood.
That's true. So it's an insulator, right? So I don't know what we've been at this, maybe 5 minutes. The metal has totally melted the ice cube. The plastic, not so much, and the wood, pretty much not at all. Now, you could have your students time this if you wanted to, but it's going to get a little boring after it's melted on the metal because there'll be a half an hour waiting for it to melt on the other materials. So-
David, they said, then you're saying it takes more energy to change the temperature of wood. That's why it has a higher specific heat.
A higher specific heat. So in the notes for this, I just point out metals in general have a lower heat capacity. There's a lot of variation, but it's a measure of how much energy it takes to raise the temperature of the material by 1 Celsius degree. By 1 Celsius degree. So that means that they readily transfer heat from colder objects or transfer heat to colder objects. So, there's nothing really quantitative in this little demo. It is meant to just convey, again, the transfer of heat energy from one material to another and how effective that is. Ravi, do you have anything you want to add?
Yeah, maybe you could put a note on why you chose them of almost same dimensions and all that. Would mass be a factor or would the dimensions be a factor?
Well, I chose them to be the same dimension so that students couldn't argue that it would change, that the difference would be the result of size. Because it would. If we had, if they were not the same, it would just be introducing another variable. If they weren't the same size, then size could be an argument. We kept them the same size so that we can compare relatively the same relative amounts of material. Good point.
Because some students could say that masses are different.
The masses are certainly different, yes.
So 2 comments. They said in 6th grade, they teach about conductivity of metals, metalloids, nonmetals. I wonder if it might be a good to use aluminum, silicon, and carbon. And, I think you got to decide what's best for what you're doing. And then the other one was when talking about conductors and insulators, I usually talk about the atoms in conductors being more closely packed together than those in insulators. Would that be correct? By this point, they are not familiar with heat capacity.
I don't think I would say that that's correct. I think that would, I wouldn't say that's correct. I don't think it matters how closely packed the atoms are. I think there are other factors that come into play.
At a high school level, you can talk about free electrons. Middle school, maybe not. I think the heat transfer is because of free electron flow or something.
Were there any other questions? This is the kind of activity I would do before I did the other experiments, because I think it's just a way to get kids to think about conductors and insulators and heat transfer. And particularly because it's, totally non-mathematical.
So do you send the teachers this one?
Yes, they did get one of those. Okay. Can I move on to something maybe more engaging?
Well, there's been a couple. So do you go into the world of heat, I'm going to say hot and cold, Cold being the lack of heat and cold, and or why the aluminum feels cold. And I'm going to answer that. I think yes, you do. You know, you can talk a lot about why certain things feel. I used to do a thing called "Is your hand a good thermometer?" And I would have kids go around the room and touch different things and try to come up with a hierarchy of hottest to coldest in the room.
Yes.
You know, and then have them go back with a, you know, IR thermometer and actually get the temperatures. And then I think it's good for them to kind of then have a discussion trying to figure out why certain things felt colder and what that means. And I think that's kind of what you're doing a little bit here too as well.
Okay. So think about what your hand is. Your hand is warm. And when it touches the metal feels cold. What's happening to cause your hand to feel cold? Who's got an answer for that? In terms of heat transfer, what is happening when you touch the metal that causes your hand to feel cold?
Heat is leaving your hand.
Yeah. So as you just said, your hand a good thermometer. So my hand is warm. I touch the metal. Now my hand feels cold. What happened? This is simplistic, but what happened to the heat that was in my hand? It went to the metal. Remember, energy is transferred, heat energy is transferred out of hotter regions to cold regions. So when I touch the metal, my hand feels cold. The heat went from my hand into the metal. The metal's a good conductor. When I touch the wood, it feels warm. What's happened? Why does my hand feel warm? What's happening to the heat in my hand when I touch the wood?
Staying where it is.
Yeah,
Heat is, you know,
it's
heat is leaving the wood or
the heat is being reflected back into my hand because the wood is a good insulator. So you touch a wool sweater, it feels warm. The wool sweater isn't warm, but it's a good insulator and it keeps the heat from leaving your hand the same way the wood does. Does that make sense?
yeah, they're talking among themselves a little bit too, and they're getting some good advice from each other.
Okay.
So I think we're good.
Okay. So we're going to switch gears here. I will caveat this by saying Professor Ritchie is with us, and he might be cringing in his shoes at some of the things that I've said. And if he wants to correct me on anything, I will not be offended. But he is very excited to be here today to talk about Stirling engines. And one of his passions is heat, temperature, energy, thermal stuff. And he's got quite a collection of toys that we're going to show you. So if you are one of the people that received the materials from us, you got a Stirling engine. And he has one here. And he's going to demonstrate that. In fact, there is the little device, and he'll tell you how and why it works. So, Professor Ritchie, we're going to plug in the remote cam and put you on cam number 2. And I will get out of your way.
Place to plug it back here.
And I'm going to get some paper towel to clean up the water.
So you're done with the ice.
I'm done with the ice.
Okay.
So Richie, I can be around to help you out.
Yeah, exactly. I'll point the thing to aim that at it.
So in way of introduction, we have Professor Ken Ritchie, who is a full professor here in Purdue Physics and Astronomy. And you'll see him on camera here shortly. And when I say he's a really cool guy, it is not related to temperature. That's a joke.
Hey. So I want to talk about Stirling engines and that. And so what I've brought with me is a couple of different types of engines. And I want to talk a bit about the history of engines and then go into how the Stirling engine actually works and why it does what it does.
Ken, I'm going to stop you for just a minute.
Sure.
And give you a little more height here.
Sounds good.
On our camera view.
Yeah, that's much.
Okay.
That'll work.
How's that? Is that okay?
That'll work. So the history of engines. The first sort of commercially useful engine to give us a time scale was made in 1712 by Thomas Newman, which was an atmospheric engine, which just means that the force of the atmosphere was moving the engine. It was a steam engine of types. And I've got here a later version of a steam engine. The high pressure steam engines like they used in locomotives was developed in about 1800. So this is a locomotive style steam engine. And we all, I think, have an idea of how a steam engine works. You boil water inside of some big boiler, which is here. That's plugged in, so it's heating up. And that'll go out to a piston that's sitting here. That piston, then you boil the water, it increases the pressure, that pushes the piston. And generally, a design like this, it pushes the piston, but from one side, and then it opens a valve to let the steam out. And at the same time, it switches a valve so the steam pushes it from this side. Then that opens the valve, lets that steam out, and switches it around and pushes it this side. So it keeps pushing the steam on the other side, letting the steam out at the end each time. And this is just beginning to boil. So this should pretty soon start to run. Once it gets going, the steam keeps it going. The earliest engine, the one by I think his name is Newman, was actually using the fact they would boil steam inside of a piston and then spritz water into it to condense it. That lowered the pressure, which is why it's called an atmospheric engine. With a low pressure inside, the high pressure of the atmosphere would push the piston. And so that's what was pushing it. You were making a vacuum inside and letting the atmosphere push the piston. It wasn't until sort of 1800s where they thought, okay, what we're going to do is get the steam itself to do the pushing. And it's almost hot enough. There we go.
Do I get the camera closer?
Sure. So that's just your basic steam engine, right? So it's the piston is sitting here, the boiler's here, and it's just creating steam that's pushing the engine, which is working a lot like that hand boiler was doing. So let's turn this thing off. It makes a lot of noise. Let me just,
Steam getting released here.
yeah.
Oh.
That's how the whistle works on a locomotive.
I can also see water boiling.
Yeah, and this is how you get the whistle on a locomotive. They have extra steam, so it goes. So it's a steam release from it. But this is the same thing that's going on with the hand boiler, right? You're increasing the volume of some gas by increasing its temperature, which is increasing its pressure. That pressure then pushes against the piston, which then moves it. And then it's just mechanics of how you turn that into a circular motion at that point. But these are sort of steam engines. What the Stirling engine is, which was made in 1816 by Stirling, is this. This is a slightly more fancy version than the one everybody has. So let me start this one up before I talk about it.
Can I move closer?
Sure. So what we've got here in this engine, there's two sides to it. There's a hot side and a cold side. And I've got a flame going here to heat it. You'll note there's no liquid in this anywhere. This is strictly trapped gas. Gas is trapped here, gas is trapped here. And there is a wheel that runs two cams that are slightly off angle to each other. And so there's a point I can set it here where the volume of gas is small. And if I go 180 degrees, I get a point where the total volume of gas is large. Then I go back to a total volume of gas that's small. And there's a point here where I'm transferring at essentially constant volume. I'm moving the gas from one point to the other. And so there's what you're doing with this engine is, once it gets going, is taking gas that's trapped here in a small volume, heating it up so it gets to high pressure. That will push the piston. You then transfer the gas over to here and then let it cool down. When it cools down, atmospheric pressure will push the piston back. And then you transfer it back over to here and heat it up again. And you keep doing that over and over again. And you get an engine again. So it's a trapped gas that is getting heated here, cooled here, and you're just taking it here at one volume, heating it up, letting it expand, moving it over here, cooling it down, letting it contract, moving it back over to, get my hands in here. So you're taking it in some volume, heating it up, then letting it expand, moving it to the cold side, cooling it down, and then letting it contract, moving it back over, heating it up, letting it expand, moving it back over, cooling it down, letting it contract, doing that over and over again. And that's how a Stirling engine works.
Can I pause you for a second?
Sure.
So Christy, I hope that answered your question. And she said, is it making the chamber smaller and larger? Well, the chambers are getting smaller and larger, but it's because of what's happening with you're heating the
Well, the chambers
gas.
are smaller and larger by the mechanics of the system.
Okay.
So it is the way the cams are set up. The two pistons move at different times, and by moving at different times, you get a point where they're both at the bottom and a point where they're both at the top. And so you get a small volume and a large volume, as opposed to something doing this, which would always have the same volume. By doing it at a slightly different angle, you change the volume as you go along. So the mechanics are setting the volume here. You can draw this. You can draw a nice diagram for this to explain what's going on.
And David, as a side note, when he's done, if you take a picture of that, we can add that to the website so that we have that as a.
Can do. So this is what's known as a PV diagram. So you got pressure on the y-axis, you got a volume on the x-axis. And what we're doing is we're starting here at a low volume and increasing the temperature, but keeping the volume constant. That goes to a high temperature. You then transfer it at a constant temperature. You let the piston move. So now the pressure makes the volume get larger and the pressure smaller, but keeps the temperature constant. You then, when you're over here, cool the gas, which makes the volume smaller. You then, at constant temperature, move it back over to here and heat it up again. And so you're going around this cycle. And as a matter of fact, if you integrate this, the area inside the curve is the amount of work you get out of the system. But this is the way you look at engines. So this has two what you call isochoric parts and two isothermal parts. So there's a constant volume, constant temperature, constant volume, constant temperature. And it goes around that cycle. And this is required for an engine. If an engine doesn't cycle, you run out. It has to be able to cycle back to the starting point each time. If not, it's not an engine. It's just something falling. So that's the Stirling engine. And that's what we sent out to everybody, or Dave sent out to everybody. Let me grab. So I've just got a cup of hot coffee. Blow up that. So what I've got here is just a cup of hot water, which could be a cup of coffee. It works. And what was sent out to everybody, got them, were these small Stirling engines. So this is the same as this larger engine sitting here, just different sort of setup for it. You put that on just a cup of hot coffee, wait a bit for it to heat up. It'll start going. And so what's happening there is, this is your hot side, this is your cold side, and in the middle of this is a piece of styrofoam that's going up and down, which is making the gas shift from the hot side to the cold side to the hot side to the cold side. At the same time, you have a little piston right here, which is setting the volume each time. So when it's on the hot side, it's at the small volume. When it's at the cold side, it's at the high volume. And so this is the volume change here, and this is what shifts it between the hot and cold side each time.
We got a couple questions and a couple comments. And so, David, this might be something we got to do later, but they tried to put theirs together and the pistons do not stay attached. They said the side view picture for assembly is lacking. Can you go over which direction the arms should be facing for assembly?
So the way it should be assembled.
Let me get one that's not assembled.
Oh yeah, we've got one I can assemble, so I can show you how it goes together. So we'll grab one and put one together right here. Now, as for the piston coming off, if they mean that it's not connecting to the cam here, this has to sort of snap in. And it sort of has to really snap into there. And it was kind of annoying to snap it in there. So it may be that it's not fully snapped in. If it's letting you go at this end, down at the bottom here, then I don't know. But if it's at the top, just push it a bit harder. It'll snap in.
And someone else chimed in and said, you got to give the clips a bit of pressure. It feels like you're going to break them.
Yeah, that's the thing here. Yeah, it's a good little shove to get these.
Does the direction matter? I don't know what.
No. What does matter is that it lines up like this. So this cam, the one that's furthest away from the wheel is right over top of the piston. The one that's right next to the wheel is over the middle of the two cams are off-centered from the wheel. And so the closest one should be on the side right above the piston going into the body, and the other one should line up right above the piston on the outside.
Could the C's face the same direction or opposite?
Does not matter.
Here we go. We've never been out of the box.
And so we've got one that's never been out of the box before. So we'll give it a shot, putting it together, and see if I can break this one. So there's the wheel thing that you get, right? And one of the cams is further away and the other side is close to it. So this one's close, this one's further away. So I'm going to leave that sort of there, knowing that there's a asymmetry to that.
We're making a lot of people happy right now. They're getting theirs finally working. So thank you so much.
And then this part of the setup, away. So now here you have a little, let's get closer to the thing. You have a clip here you can just pull out and get out of the way. So that clip, toss that. You have this here and you've got this one here. So you have one coming off, I'll say the white piston, and then one coming out of the middle of the body right here. And the way mine's set up, although I say it does not matter, mine, the one coming out of here, the C is this way, the one coming out of here, the C is this way, but it really should not matter which way the C's go. That's the way mine's set up. So I'm just going to leave these so that the open part of the C points towards the here.
You dropped your hands down. Thank you.
So it's easiest to, so the open point of the C of both of these points towards where the axis is going to be. It's just the easy way to do it. And then this gets put in again so that the one cam is over this sort of white piston, and the other cam's over the center of the entire cylinder piece at the bottom. Then all you got to do, down slowly, take this C, this little thing here from the center. Get it to so that it's over top, and then push it on. I don't know if you can hear the snap, but it did snap into place when I got it there. And now you can see that one is moving up and down. It's pulling it up and down. I haven't connected the other side yet. The other side, same thing. Gonna pull this up. Pull this up. So I have this. There, I get this. Get it nice and close there, and then I just got to snap it in. There, snapped in. So if I take mine off of here, put this onto the heat. Takes it a second for that side to get hot enough for this to run. And they only run in one direction, and I can never remember which direction it runs in. So if it's not working, try the other direction. There we go. It is running. It'll get going faster.
Thank you very much. That was big help. And for those of you, I put the link in for people who wanted to order them. I put the link in where we purchased them. And yeah, they're about $40. So there you go.
And so what's happening is exactly what's happening on this bigger, more fancy schmancy one, is you are shifting gas between these two areas. And you can see if you look at it sideways, you can see that there is that going up and down. And that piece of styrofoam going up and down is what's making two chambers. The top's cold, the bottom's hot, and it's just shifting gas from being mostly on top or mostly on the bottom. The other thing you can do, which works, and we'll see if it works with this one.
Oh, here the bottom is cold and the top is hot.
Yeah,
Right?
so this is a big beaker full of ice and water. I may need a little bit more water in there.
That's nice here.
What you want to do if you're going to use ice on the bottom instead of heat is you want to make sure the water contacts the bottom of this. Yeah.
Would it run the opposite this time?
And now it should run the other direction.
Oh, okay. Interesting.
So let me get these both set up in the same setup. Over here. This may take a while because the bottom of this was still hot because it used to be on top of that. So I've got to cool the bottom down. It is working. So yeah, that's running on its own now. So that is the same thing going on, except now the hot side is the room and the cold side is the water. Whereas in this one, the hot side is the water and the cold side is the room. It's just a change in temperature that matters. So if this is hotter than this, that's the hot side. And then it'll run in the opposite direction because it's got to have, whether it's got the large or the small amount of volume at the hot or cold side, depends on which way the cams run. And so I don't know if you can see that there, but this one is running this way and this one is running this way.
Yeah, you can see it on the video. It looks good.
Yeah. So that's, this is just what the reason why this one runs slower. What sets the efficiency of the motor is the change in temperature. And since we're stuck at room temperature and ice water, we can't really go much different in the change in temperature there easily. Whereas this, I can go up to all the way to boiling water compared to room temperature, which is a huge change in temperature. So this one's much faster.
I'm going to keep my hand so it won't run fast.
One could try to heat the top. Now this will run. You should be able to run this until the water comes to room temperature. The problem is that this will heat the top at some point. And that's why it's slowing down. It's more that the top of this is getting warm over time. But it'll run for a long time. And it'll run on a cup of coffee. It'll run with the ice water. It will run on top of an ice drink. The thing is, you generally have to have thermal contact for this to work. You have to have the water actually touching the bottom to get it cold enough, quick enough. Air is too good of an insulator to have that work. But yeah, so that's the basic Stirling engine. Yeah.
Have you ever done, they're asking like whether you put like tape or a color or something to try to count the revolutions. It's hard to see on the video, but if they tried to compare the revolutions of one versus the other.
One could do that and then do it as a function of the temperature of the water.
Yeah.
Yeah, one should be able to work out. Would one be able to work out from that? Because the revolutions, you should be able to figure out the energy coming out. So one, I have to think about, you could probably get the efficiency out of that. And the Stirling engine is theoretically the most efficient engine you can make. It's equivalent to a Carnot engine, which is theoretically the most efficient engine you can make. The problem is it has no torque, so you can't actually do much with it unless you make really huge engines. Although, considering this is Indiana, one of the first cars in the Indianapolis 500 back in the early 1900s actually had a Stirling engine in the car and ran the Indianapolis 500. Mm-hmm. It didn't finish, but there was a car with a Stirling engine in it that ran the Indianapolis 500. And
How did they maintain the temperature difference in that?
no idea. I have no idea how they actually ran a Stirling engine in a car in the Indianapolis 500. And obviously, they'd only ran for about 84 laps out of 500, so they didn't do a very well job at it either. Where you see Stirling engines is in ships. There are ships still made with them, mainly because a ship has enough space in the basement to make really big Stirling engines. And then they're very efficient if you got a big enough engine to get enough torque to do what you need to do. And so you can build huge engines in the bottom of a large boat, and it's really hard to do that in like a car or something like that. So you just can't get them to work in a car. So once you go past this, the next thing that was done was 1824. Carnot came up with the Carnot engine, which is almost the same as the Stirling engine, which remember was this: 2 isochoric parts and 2 isothermal parts. When one gets to the Carnot engine, the only difference is instead of being constant volume here, it was constant energy between these 2 points. So the volume changes slightly, and there's no change of energy. And the only reason why that was a huge advance was not necessarily in the making of engines, but it was in the theory of thermodynamics. You could analyze the Carnot engine easier than the Stirling engine, which advanced the theory of thermodynamics. As an interesting side point, up until mid-1800s, the theory of heat was still called the caloric theory of heat, which was that heat was a particle named a calorie. And they thought that caloric was a compound that heat was that was transferred from one object to another, and that caloric was conserved. And when Carnot worked out the heat engine, he used the caloric theory of heat and got all the right answers. Even though it's completely wrong, heat is energy, it's not its own particle. It just happens to be lucky that it worked. And so Carnot's paper on the motive force of fire in 1824 actually used the wrong theory to get the right answer. But yeah, that was one of the last uses of the caloric theory of heat. With that, and then Joule came out and showed that work and energy, or sorry, the heat and work were the same thing by the mechanical equivalent of heat that he did.
How do you spell Carnot?
Carnot.
Thank you.
And then after that, I think your kids who see this would be interested in how does this compare to a car engine, the internal combustion engine. And so what we've shown so far, this is the Stirling engine. The Carnot engine is essentially the same thing, but at constant energy, not constant volume in those 2 sides. And so you refer to this, the thermodynamics of this engine, you say it's going through a Stirling cycle. You say that the Carnot engine is going through a Carnot cycle. The steam engine actually goes through what's called the Rankine cycle. And then the car engine goes through the Otto cycle, which is OTTO, not automobile auto. It's the guy's name, OTTO. And the Otto cycle is a cycle that allows for the input and exhaust of the internal combustion part, the fuel. So it's essentially the same idea as these engines here, except these are trapped gas. So none of the gas leaves this engine ever. Whereas in an internal combustion, right, you bring in fuel at low pressure, at atmospheric pressure. You then close the valve. You then compress the gas that's in there to a small volume, high pressure. You then ignite it so that it becomes high pressure. That pushes the piston away, which is your power stroke. It then comes back. The valve opens. When it comes back, it expels all the gas and goes back to atmospheric pressure. That valve closes, and the original valve opens again, and you bring in new fuel. Close the valve, compress, bang, back up, get rid of, open back up, bring more fuel in. So it's the same kind of idea, except you're creating the high pressure by igniting the gas inside the engine, as opposed to here where you're just heating it from externally. And that's why it's an internal combustion engine, but that's the Otto cycle. So they all are similar, and it looks very similar to this cycle here, except you have a piece in the bottom where you bring in and out your gases. But it's very close to a Stirling engine in that sense.
Dr. Ritchie, would this be called as an external combustion engine? Can you call it?
Yeah. Well, what they generally refer to these is a I refer to them as trapped gas engines, in the sense that there's nothing inside that ever comes out, and you couldn't do an internal combustion if you didn't replenish the fuel. So I don't think people generally refer to it as an external combustion engine. They tend to refer to it as a trapped gas, because then you can't do it again, because you have to get back to the start of the cycle each time, and if you don't come back to the same point, you spiral out of control. And so you have to have a cycle that always comes back to the starting point.
I want to ask you about the diagram, if I may.
Sure.
You said there's an isothermal part
Yes.
and an isocoric.
Choric.
And explain what those terms mean for us.
So isothermal is just constant temperature. Isocoric is the fancy schmancy term for constant volume.
Okay.
If it's constant pressure, it's isobaric. If it's constant energy, it's adiabatic. And those are all the fancy terms for that. So if you do the so you refer to this as two isotherms and two isocores, whereas the Carnot engine is two isotherms and two adiabats.
What do you want to show to the audience? Like okay. Yeah, these are the two. This is the isocoric part, constant volume. This as well, and this is isotherm. Dr. Ritchie referred to the isotherm. This is another isotherm. So this is an isothermal expansion. This is an isothermal compression.
And then, of course, I draw this as the theory. It's not exactly that. If I were to draw what it was actually doing, paper. I'll do it in green. I'll just do it on. I'll do it.
Oh.
It actually does something more like that in reality. It's not as sharp at the edges. This is because we're doing a piston moving things around. It's almost a straight line over here because it's like a sine, the top of a sine curve. And it's almost a straight line over here, and it's almost the same here, and but it's not really. It's really quite a bit off from the theory. But the theory is easy. If you think of this as what's going on, it's real easy to analyze it from a theory standpoint. And it's certainly what we always draw, even though that's not what really happens.
I'm going to give you all a resource. If you are wanting to know a little bit more about Sadie Carnot and the Carnot engine and related topics, Google Mechanical Universe, Carnot engine, and you will find on YouTube, you'll go down the wormhole of watching Mechanical Universe for 30 hours, but it's a wealth of information about everything physics. So physics and mechanics. So, but I recall the episode on the Carnot engine, and it was quite fascinating. And at that time, over my head, but I think you'd find it interesting. So, Mechanical Universe on YouTube.
So a great question was asked by Christy, and she's asking the other teachers, how does everyone think they will use this? So I think it's a great, and a lot of teachers were talking about having it sit up on their desk for kids to ask questions and start, the whole conversation. But then at the end of the day, they're going to have to hit standards and start talking about it. So I'm giving them a chance to kind of throw ideas out at each other and how they would use this in their classroom.
Are we getting ideas?
Yes. Yeah, I'm just letting them. Give them a minute to share a little bit.
Okay.
So while they're sharing, Dr. Ritchie, if you don't mind, because I think this is always a fascinating, how did you end up where you are?
So I had an older brother who was a chemist, and that certainly drew me to science early on. But at some point in high school, in my rebellion years, I decided to become an artist. And I was all ready to go to the Ontario College of Art, because I grew up in Ontario, in Canada. And me and a buddy had all planned out, get the party apartment in Toronto at the Ontario College of Art, and spend 4 years at the College of Art partying, and probably fail out and start a punk band or something. And then he failed out of high school, so I couldn't go in with him that year. So I stuck around, and in Ontario at the time there was a grade 13 that you needed to go to university. So I stuck around for one more year so we could try to pass grade 12. And then ended up getting into physics then. That got me into the physics department from there, because in a little bit of the rebellion against my brother, I ended up doing physics instead of chemistry. And then to get into what I'm doing now, which is sort of my real research is single molecule biophysics. When I was in second year, I got what's sort of the equivalent of a summer research fellowship. And they said, what do you want to do? And at the time I was thinking, I want to do, sort of high energy elementary particle stuff. And at the school I was at, the University of Waterloo, there was something listed as atomic and molecular. And I thought, that's close. That's as close as they got was atomic. And I put it down, and I ended up working in a group trying to work out the specific heat of proteins. And I ended up staying in biological physics ever since then. And that's where I started really getting my passion for thermodynamics, was trying to calculate and measure the specific heat of proteins.
I think that's just amazing that you went from, and not that, but you went from an art major to end up in physics, which, I mean, and this is what I keep telling teachers and kids, you never know where you're going to end up. You just got to keep going and finding your passion. And then eventually you're going to end up where, as long as you're not afraid to keep, broadening your horizon.
Yeah, and I keep telling even students here, you're never stuck. If things aren't working out, maybe you're not in the right place. Find the right place for you, and you just got to find it. And there's no point in life where you're beyond the point of being able to change that.
Perfect. Thank you. So they shared a lot. They threw out a lot of ideas on how to use this, and I think that'll help them think through where they can do this. So, and yes, Christy, yes, thanks everyone for piping in and throwing out ideas.
Okay, so one last thing I'd like to bring up for everybody is, and then one of the reasons I think this is so fascinating. So this all sort of started at the beginning of the 1800s, and it was all trying to build a better steam engine, right? And so that was to try drive the Industrial Revolution, to try make a better locomotive. If you follow this through the history, you get to the point where they're trying to calculate specific heats, and they're trying to figure it out for gases, and it won't work. Once they can liquefy helium, all the theory breaks down. It ends up being proof that quantum mechanics existed. And you follow the whole bit of entropy and how Brownian motion works, and Einstein used that to show that atoms existed. So the initial part of trying to make a better steam engine ended up proving that quantum mechanics existed and atoms existed. So that's a pretty good blue-collar science getting to that point. So I think it does underscore that you can't necessarily predict what is important discoveries today for what will be important discoveries 30 years from now. And so in a sense, there's a bit of, you don't put funding into quantum computers only if you want quantum computers. You got to put funding into something else that may be important for quantum computing, but you don't know it yet. That's sort of the whole idea. And I think that's why you need to spread funding around everywhere. And you're never sure exactly what's important 30 years from now. And certainly the steam engine wasn't obviously going to prove that atoms existed, but it sort of was on the way to doing that. So anyway.
All right.
I'm done.
Thank you so much.
Thank you, Professor.
Yeah, the comment was, woo, that's deep.
Well, that's what we are here at Purdue. It's physics and astronomy. We're deep. Okay, I think that was a good finale for our session today. And I thank Professor Ritchie greatly for participating. Bill, I think that wraps us up here.
Okay.
We're all out of
Activities.
a lot of things to do.
Okay. So, thank you. I feel smarter just listening to you guys. Well, Tanya, I will tell you this, every time we do anything, I learn more and more. So I think that's kind of what he was talking about, that you never stop learning and there's always something else out there. So, if you, I gave the links earlier, for the website. And if nothing else, if you forget, just type in Purdue College of Science Outreach and you'll find us. And then that can take you down, like Dave was saying, down the wormhole of all the different things we have available. You can get to each of the coordinators that way. If you want to just send an email to k12science@purdue.edu, that will get you to a generic email, which will then allow us to get it to the right person. So even if you forget, like, oh, who was the physics guy? If you send it to k12science@purdue.edu, I'll make sure it gets to them. You can also just type in physics@purdue.edu or whatever. Okay. So the last thing that I have is probably about a week from now, I'll be sending out to everybody who was participating. I will send you out an email asking for some feedback and a survey that you'll be getting. Yes. And thank you, Sarah. You jumped right on that. Is there a survey we should fill out to help you collect data for your next grant? I'll be doing that as well. David just put his email in there, so people have that as so he can go straight to him as well. The last thing that I need is if you want PGP, CRUs, continuing education credits for your license, once again, just send me an email. Make sure it has your name and the last four of your SOCH, and I will get those certificates out. It probably won't be till late next week, maybe even the following week. So don't freak out if you don't get them today or tomorrow. So just make sure that you send me that email. And my phone's going nuts, so people are already emailing me. Everybody says thanks a lot, David. Thank you so much. And I want to thank everybody for being a part of this. We know that being a teacher, let alone a middle school teacher, let alone a middle school science teacher, is a tough gig at times. And we appreciate all that you do to help to help students learn science and get them excited about science. So anything, David, you want to say as we say goodbye?
No, other than thank you all for attending and let me know if I can help you. I just also want to extend a word of thanks to Ravi, who has been here throughout. He helped create some of the lesson materials, and I appreciate his help. So he'll hopefully be around here for about, another 5 or 6 years?
2 years, 3 years.
2 years, 3 years. Okay. All right.
Robbie's like, don't do that to me. I'm ready to go.
All right.
Okay.
Thank you all. Thank you very much for participating. Bye-bye.
Bye.